There is a place in the Pacific Ocean so isolated that the closest human beings to it are often astronauts orbiting hundreds of kilometers above Earth. No island, no shipping lane, no visible landmark from the surface, just ocean. Point Nemo is the single most remote location on the planet, more than 2,600 kilometers from the nearest land in every direction. The water here sits inside a slow rotating current system that cuts the region off from much of the rest of the ocean, leaving the surface strangely clear and almost empty of visible life. And yet something survives here, far below the surface, beneath nearly 4 kilometers of cold water and permanent darkness. Animals move through an environment that receives almost no nutrients from above, no sunlight, almost no plant life, almost nothing drifting down from the surface to feed what lives below. But life found a way anyway. In 1997, underwater microphones detected the loudest unexplained sound ever recorded in the ocean near these coordinates, powerful enough to be heard thousands of kilometers apart. For years, nobody could explain what produced it, and surrounding the seafloor below Point Nemo are the remains of hundreds of spacecraft deliberately crashed into the ocean because this is considered the loneliest place on Earth. The deeper scientists study this region, the stranger it becomes, not because it is filled with monsters, but because almost everything about it seems incompatible with survival, and still, the dark is alive. Tonight, we descend into the most isolated ecosystem on Earth to find out what managed to survive in a place almost completely cut off from the rest of the planet. If you're tucked in right now, phone dimmed, trying to let your brain slow down, this one was made for you. Give it a like, subscribe if you haven't, it's free, and it helps our channel more than you can imagine. And let me know in the comments, where are you watching from, and what time is it where you are? Now, let's descend into the most isolated ecosystem on Earth. Long before anyone sailed deliberately toward those coordinates, the water itself had already shaped the isolation. The emptiness surrounding Point Nemo was not created by distance alone, nor by weather, nor by the absence of islands on the horizon. It was built slowly by motion, by currents tracing enormous circles across the South Pacific for millions of years, turning the center of the ocean into a place that drifted apart from the rest of the world without ever physically separating from it. The coordinate was formally calculated in the year 1992 by a Croatian survey engineer named Hroje Lukatela, using early geospatial software to identify the exact location on Earth's surface farthest from any coastline in every direction. He named it after Captain Nemo, the solitary commander imagined by Jules Verne, a man who disappeared beneath the sea to escape human civilization entirely. The name remained strangely appropriate, not because Point Nemo hides beneath the ocean, but because the ocean above it behaves almost like a sealed world of its own. Scientifically, the region carries a colder title, the oceanic pole of inaccessibility. There is no mountain there, no trench, no reef, no visible marker separating it from the surrounding Pacific. It exists as a mathematical condition rather than a physical structure, defined only by equal remoteness from land in every direction. Yet the mathematics conceals something physical all the same. The water around Point Nemo does not circulate like most of the ocean. It turns inward upon itself. 4 immense current systems rotate clockwise around the South Pacific Basin: the South Pacific Current, the Peru Current, the South Equatorial Current, and the East Australia Current. Together they form the South Pacific Gyre, a vast circulating system large enough to span a significant portion of the planet. At its outer edges, water continues exchanging energy and chemistry with the wider ocean, but toward the center, the circulation becomes increasingly isolated. The currents act less like flowing rivers and more like moving walls, slowly preventing nutrient-rich water from entering the interior. Near coastlines elsewhere on Earth, rivers deliver minerals into the sea. Storms churn nutrients upward from depth. Continental shelves create turbulence and mixing. Tiny photosynthetic organisms bloom near the surface in enormous numbers, turning sunlight into living matter that feeds everything beneath them. At Point Nemo, much of that process weakens almost to silence. Warm surface water rotating through the gyre is continuously pushed outward, away from the center, carrying nutrients with it. What remains is an oligotrophic desert, a region so biologically starved that phytoplankton concentrations approach some of the lowest levels ever measured in the global ocean. From orbit, the water can appear intensely blue, almost unreal in its clarity. The color comes from absence. There are so few microscopic organisms suspended near the surface that sunlight passes deeper into the water before scattering back upward. In productive oceans, life itself colors the sea. Here, the scarcity of life leaves the water almost transparent. That scarcity changes everything beneath it. Most deep ocean ecosystems survive because the surface world above them is busy and alive. Dead plankton, fecal particles, shed tissue, fragments of plants and animals drift slowly downward through the darkness in a continuous fall sometimes called marine snow. Even at abyssal depths, distant ecosystems remain connected to the sunlight above through that endless rain of organic matter. Point Nemo receives almost none of it. The darkness below exists beneath an ocean desert, and this makes the region fundamentally different from nearly every other deep-sea environment on Earth. Life here cannot depend on abundance, slowly descending from the surface. It cannot rely on rich feeding grounds far above. The organisms that persist in these waters survive within one of the thinnest energy economies on the planet, adapting not merely to darkness and pressure, but to absence itself, shaping entire bodies and behaviors around the reality that almost nothing ever arrives from above. A drifting particle of organic matter falling through the water above Point Nemo does not move through a single ocean. It passes instead through separate worlds layered one beneath another, descending slowly across invisible boundaries that divide temperature from cold, light from darkness, abundance from scarcity. The descent can take weeks, sometimes months. During that entire journey, the particle sinks through regions so physically different from one another that they resemble stacked ecosystems more than a continuous body of water. Near the surface, in the epipelagic zone, sunlight still penetrates the sea. The upper few hundred meters hold the last direct connection to the sky above, where waves scatter daylight downward in pale, shifting bands. In most oceans, this layer is crowded with microscopic life. Phytoplankton drift near the surface, converting solar energy into living tissue, forming the beginning of nearly every marine food chain on Earth. At Point Nemo, the same process exists, but faintly, reduced almost to a whisper by the starvation of the gyre. The water remains unusually clear because there are so few suspended organisms to interrupt the light passing through it. Yet even here, in one of the least productive surface environments on the planet, life still persists in scattered forms, thin populations moving through immense volumes of open water. Far below, between roughly 200 and 1,000 meters, the mesopelagic begins. The descent into this region is gradual enough that no exact border exists. Blue light weakens first, then dissolves into dimness, so slowly that the transition can feel almost geological in pace. Pressure increases continuously as the water deepens, reaching around 100 atmospheres by the lower boundary of the zone. Human lungs, blood vessels, and bones were never built for such conditions, but the organisms living here experience the pressure not as violence, only as the permanent structure of existence itself. This layer contains the greatest biomass of vertebrate animals on Earth. Vast populations move through it every day and every night, though almost none have ever been observed directly in their natural environment by human eyes. Most remain known only through fragments brought upward in nets, flashes captured by submersible cameras, or acoustic signatures drifting through the dark. Many spend daylight hours deeper in the water column before ascending again under cover of night, forming enormous migrations hidden entirely beneath the surface of the sea. Below 1,000 meters, sunlight disappears completely. No weather reaches this depth, no sunrise arrives. The bathypelagic zone begins here, extending downward toward the abyssal plain beneath Point Nemo. Temperatures settle into near permanence, hovering between roughly 1 and 4 degrees Celsius throughout the year, with deep waters around the seafloor often remaining only slightly above the freezing point of seawater itself. Salt suppresses that freezing threshold to approximately minus 1.8 degrees, allowing liquid darkness to persist in a narrow thermal margin between motion and ice. Pressure at 3,800 meters reaches nearly 5,600 pounds against every square inch of matter. The force surrounding a body there resembles the weight of a small automobile resting upon an area no larger than a postage stamp, repeated endlessly across every surface simultaneously. Yet most deep-sea organisms contain almost no rigid internal air spaces for pressure to crush. Their tissues bend with the water around them, soft and fluid, shaped by millions of years within an environment where flexibility became more valuable than strength. The darkness in these depths differs fundamentally from anything known at the surface. It is not the temporary darkness of a room after sunset, nor the muted darkness beneath storm clouds. It is the total absence of photons from the sun. No natural daylight has touched the seafloor beneath Point Nemo for millions of years. Eyes evolved for surface life would perceive nothing there at all. And within each layer, isolated by pressure, chemistry, oxygen concentration, and light, separate communities continue their slow existence, suspended one beneath another through nearly 4 kilometers of water, each adapted not merely to the ocean, but to a precise depth within it. Every evening, long after the horizon above Point Nemo has dimmed into darkness, the water column begins to move, not with the violence of storms or the turning force of currents, but with countless small bodies rising together through the mesopelagic depths in one of the largest synchronized movements on Earth. The migration happens silently, beyond the reach of moonlight, hidden inside the enormous vertical distances beneath the open Pacific. Most of it has never been witnessed directly by any human observer, yet it happens every night without interruption, as steadily as tides. The animals making this ascent are lanternfish, members of the family Myctophidae, small vertebrates usually no longer than a human finger, though their total collective biomass exceeds almost anything else alive in the ocean. There are more than 200 known species, distributed across nearly every major marine basin on the planet. Taken together, their estimated weight reaches somewhere between 550 million and 1 billion metric tons, greater than the combined mass of most global commercial fisheries. Entire populations drift through the dark in numbers so immense that sonar systems sometimes mistake them for the seafloor itself. During daylight hours, lanternfish remain deeper in the water column, typically between 200 and 1,000 meters below the surface. At those depths, the remaining traces of sunlight fade into a dim blue haze, barely detectable through adapted eyes. Pressure increases steadily around them, while predators searching visually from above struggle to distinguish their silhouettes against the darkness. The fish wait there throughout the day, conserving energy in colder water where metabolic demands slow slightly, suspended in vast diffuse layers spread across the Pacific. Then night arrives at the surface. As darkness deepens overhead, the lanternfish begin rising upward through hundreds of meters of water. The movement is not directed by conscious coordination or social command. Each individual responds instinctively to light intensity itself, ascending only when the fading brightness above becomes dim enough to conceal its body from larger hunters. By midnight, enormous portions of the global lanternfish population have moved into shallower depths to feed on zooplankton and drifting microscopic organisms near the upper ocean. Before dawn, the migration reverses. As the first traces of sunlight return to the sea above, the fish descend once more into deeper water, retreating from illumination with remarkable precision. Every day of their lives follows this rhythm, upward in darkness, downward in light, repeating continuously across entire oceans for millions of years. Their bodies carry another adaptation to the darkness around them. Along their flanks and bellies sit rows of bioluminescent organs called photophores, each species arranged in subtly different patterns. Researchers identify lanternfish species partly by these configurations alone, much the way fingerprints distinguish one human from another. The lights themselves produce faint blue illumination through biochemical reactions occurring inside specialized tissues, creating signals and camouflage within the dim mesopelagic world. Many species use the glow for counter-illumination, predators below searching upward for silhouettes against the faint surface light encounter, instead a soft matching radiance emitted from the fish's underside, reducing the contrast of its body against the water above. The lanternfish becomes difficult to distinguish from the remaining traces of filtered light descending through the sea. In darkness, survival often depends less on speed than on disappearing completely. Their migration alters the chemistry of the ocean itself. Feeding near the surface and returning downward each day, lanternfish transport carbon from shallower ecosystems into deeper waters through respiration and waste. Billions of small bodies repeating this cycle nightly create a biological conveyor carrying organic material toward the deep ocean interior. The process occurs on such an enormous scale that it rivals some physical circulation systems of the sea. In the waters surrounding Point Nemo, the migration continues, though more sparsely than in nutrient-rich regions elsewhere in the Pacific. The starving surface above the gyre cannot support the same density of life found nearer productive coastlines or colder upwelling zones. The lanternfish thin outward into the emptiness, becoming more scattered as the center of the gyre approaches. Yet even here, in one of the least fertile stretches of ocean on Earth, countless small lights still rise and descend through the darkness every night, carrying the faint remains of the surface world slowly downward through the deep. At certain depths beneath Point Nemo, an animal moving through the water can briefly reveal itself without ever touching sunlight. A pulse flickers somewhere in the dark, then disappears. Farther away, another responds, softer this time, like a distant signal crossing empty water. The light lasts only seconds, sometimes less, but across the deep ocean these flashes occur constantly, scattered through the water column like fragments of a silent language, exchanged in darkness. Below roughly 200 meters, sunlight no longer reaches with enough strength to matter. In this region, bioluminescence becomes one of the defining features of life itself. Scientists estimate that the majority of marine species living in the deeper pelagic zones are capable of producing their own light. In the world beneath the gyre, illumination is no longer borrowed from the sun, It is generated directly by living tissue. The chemistry responsible is remarkably delicate. A molecule known as luciferin reacts with an enzyme called luciferase in the presence of oxygen, releasing energy not as heat, but as photons. The result is a cold radiance of extraordinary efficiency, producing almost no wasted thermal energy. Evolution discovered this mechanism independently across dozens of unrelated branches of life, from fish to jellyfish to plankton, each lineage arriving separately at the same solution to darkness. Most deep ocean bioluminescence appears blue or blue-green. These wavelengths travel farther through seawater before being absorbed, moving through the ocean with greater efficiency than red or yellow light. Over immense spans of evolutionary time, the physical properties of water itself shape the color of living illumination. The sea selected which photons survived the farthest journey. For many mesopelagic animals, light functions primarily as camouflage. Along the undersides of their bodies, specialized organs emit faint glows, matching the residual illumination filtering weakly downward from the surface far above. Predators searching upward for silhouettes encounter only a dim continuation of the water above them. The animal erases its outline by reproducing the ocean's own fading light, becoming almost impossible to distinguish from the darkness surrounding it. Some species turn bioluminescence towards stranger purposes. Dragonfish of the genus Malacosteus produce red light, an unusual wavelength nearly invisible to most deep-sea organisms. At the same time, the dragonfish evolved eyes capable of detecting that same red glow. In practical terms, this grants the animal a private hunting beam, moving through darkness unseen by surrounding prey. Small organisms drifting nearby remain unaware they have already been illuminated. Elsewhere in the water column, the jellyfish Atolla wyvilli uses light defensively rather than concealment. When attacked, its body erupts into rotating rings of blue luminescence, spreading around the bell in expanding patterns. The display does not frighten predators away. Instead, it attracts larger hunters toward the disturbance, effectively turning the attack itself into a signal. In the deep ocean, survival sometimes depends on redirecting danger towards something even more dangerous. Colonial siphonophores, drifting through open water in bodies that can extend longer than many whales, produce synchronized pulses traveling across their entire length. When disturbed, waves of blue light race along connected chains of zooids, suspended through the dark like living electrical currents. Even microscopic organisms participate in the illumination. Dinoflagellates flash briefly when displaced by movement in the water, meaning the passage of a swimming body can leave behind luminous turbulence, trailing momentarily through the sea. The darkness beneath Point Nemo is therefore never entirely empty. It flickers intermittently with signals, disguises, warnings, hunting lures, and accidental bursts of light generated by contact alone. Most of these flashes occur without witness, exchanged between organisms drifting through the remote Pacific beneath kilometers of open water. In that immense hidden space, bioluminescence has become less an unusual adaptation than the primary visual language of life itself, a world where bodies speak by briefly turning themselves into light. There are regions of the deep Pacific where even many specialized predators struggle to remain alive for long. The water holds so little dissolved oxygen that metabolism itself becomes difficult, as though the ocean were slowly withholding breath from everything suspended within it. In these dim layers beneath Point Nemo, where sinking organic matter decomposes faster than circulation can replenish the surrounding chemistry, most active hunters thin away into absence. Yet drifting quietly through this inhospitable water is an animal that made the oxygen minimum zone its permanent home. Its scientific name is Vampiroteuthis infernalis, translated loosely as the vampire squid from hell, though the creature bears little resemblance to the violent image its name suggests. It is neither a true squid nor a true octopus. Instead, it belongs to its own ancient order, Vampiromorphidae, a lineage separated from other living cephalopods long before modern squids and octopuses diverged from one another. In evolutionary terms, it occupies a solitary branch of the tree, a survivor from a much older arrangement of deep ocean life. The animal itself remains relatively small, usually around 30 centimeters in total length, suspended between depths of roughly 500 and 3,000 meters. Its body is dark, gelatinous, and soft, with a cloak of webbing stretched between elongated arms. Delicate filaments extend from within hidden pockets near the arms, thinner than feeding tentacles and capable of drifting outward through the surrounding water with almost no visible motion. The oxygen minimum zone surrounding it forms through a slow imbalance in ocean chemistry. Organic particles descending from shallower waters are consumed by bacteria as they sink, and that decomposition steadily removes oxygen from the water column. In some regions, dissolved oxygen concentrations fall to levels low enough to suffocate most active marine animals. Near the surface, seawater commonly contains 7 or 8 milliliters of oxygen per liter. Within the most depleted portions of the oxygen minimum zone, concentrations can fall below half a milliliter. The vampire squid survives there because its blood carries an unusually efficient form of hemocyanin, the copper-based respiratory pigment shared by many cephalopods. Its molecules bind oxygen with extraordinary affinity, extracting enough dissolved gas from the water to sustain metabolism where many predators cannot function effectively. The oxygen-poor layer becomes a refuge precisely because so few competitors are capable of enduring it. Unlike nearly every other known cephalopod, the vampire squid does not actively hunt. Octopuses stalk prey. Squids pursue fish through open water with bursts of speed and complex nervous systems adapted for predation. The vampire squid abandoned that strategy entirely. Instead, it survives by harvesting what the upper ocean loses. Its retractile filaments drift passively through the surrounding water, collecting fragments of marine snow as they descend from above. Dead plankton cells, microscopic fecal pellets, shed exoskeletons, bacterial aggregates, and the dissolving remains of countless drifting organisms become trapped against mucus-coated surfaces. The vampire squid draws the material inward slowly and consumes it piece by piece. In a region where energy is scarce, it survives not by chasing life, but by gathering the leftovers of distant ecosystems far overhead. At Point Nemo, even this sparse rain is thinner than in most of the deep ocean. The nutrient-starved gyre above produces comparatively little biological material, leaving fewer particles to drift downward into the depths below. The vampire squid persists there anyway, conserving energy with remarkable efficiency, floating almost motionless for long stretches of time as the deep current carries faint nourishment toward its waiting filaments. Its eyes are enormous relative to the size of its body, among the largest proportional eyes known in the animal kingdom. In the dim chemistry of the oxygen minimum zone, they detect the faintest remaining traces of bioluminescent movement around them, and when threatened, the animal performs one final transformation. The webbed arms invert upward over the body, enclosing it inside a dark, protective cloak, while rows of soft cirri become exposed along the inner surface. The drifting cephalopod briefly reshapes itself into a closed, spined sphere, suspended silently within the cold, depleted water where few other animals can remain alive for long. Somewhere in the open Pacific, a sperm whale may surface carrying dozens of pale circular scars across its dark skin, each one smooth-edged and strangely precise, as though pieces of the animal had been removed with a mechanical tool rather than teeth. Great white sharks carry similar marks. So do dolphins, tuna, and large pelagic fish moving through tropical and subtropical waters around the world. Even a United States Navy submarine once returned to port with a perfectly circular section gouged from the rubber coating protecting its sonar dome. The animal responsible for all of these wounds is smaller than most household cats. The cookie-cutter shark, Isistius brasiliensis, rarely exceeds half a meter in length. In the immense water column surrounding Point Nemo, it drifts through darkness almost unnoticed, slender-bodied and relatively slow-moving. Yet few predators in the open ocean exploit large animals with greater efficiency. It does not chase prey across long distances or overpower struggling victims through strength. Instead, it removes small pieces from creatures vastly larger than itself, taking concentrated packages of muscle and fat before disappearing back into the dark water. Its body is shaped for stealth rather than speed. Along most of its underside, the shark produces a faint bioluminescent glow, matching the dim residual light filtering downward from above. This illumination conceals its outline from animals searching upward through the water column. Across the throat, however, the shark carries a narrow, dark band where no light is produced. Against the surrounding glow, the band creates the appearance of a much smaller fish silhouetted in the distance, an easy target suspended alone in open water. Larger predators approach. When the moment arrives, the cookie-cutter attacks from below. Thick muscular lips create powerful suction against the body of the target animal, locking the shark into place even against moving skin or blubber. Its lower jaw contains a single row of unusually large triangular teeth, fitted tightly together like interlocking blades. Relative to jaw size, they are among the largest teeth possessed by any known shark species. Once attached, the cookie-cutter twists its entire body in a rapid rotating motion, carving a nearly perfect circular plug of flesh from its victim before releasing and drifting away with the removed tissue held inside its mouth. The wound is rarely fatal. Large whales continue migrating with dozens of scars accumulated across years or decades. The shark does not require the death of the host animal. By removing only a small amount of tissue at a time, it extracts a high-energy meal while avoiding the risks associated with pursuing dangerous prey directly. The strategy allows a predator scarcely larger than a human forearm to feed successfully on some of the largest vertebrates alive. Its teeth are replaced in an unusual way as well. Most sharks lose individual teeth continuously throughout life, replacing them one by one from rows positioned farther back inside the jaw. The cookie-cutter sheds the entire lower tooth row as a single connected unit. Rather than discarding it, the shark swallows the detached plate whole, recycling valuable calcium and minerals back into its own body within an environment where resources are often limited. Like many inhabitants of the mesopelagic, the cookie-cutter performs a daily vertical migration through the water column. During daylight hours, it remains deeper beneath the surface, concealed within darker water. At night, it rises upward again, moving into shallower depths where large pelagic animals travel and feed. This nightly ascent grants the shark access to an extraordinary variety of prey moving through the Pacific, from tuna and dolphins to enormous whales crossing ocean basins. Its presence has been confirmed throughout broad regions of the South Pacific, including waters surrounding Point Nemo. There, Within one of the emptiest stretches of ocean on Earth, the cookiecutter continues its quiet existence among the migratory animals passing through the gyre. Most encounters leave behind only scars, smooth circular impressions carried invisibly beneath the surface by creatures that survived the attack and continued on through the dark Pacific with small pieces of themselves missing. In the year 2020, a remotely operated vehicle descending through the Ningaloo Canyons off Western Australia encountered something so long that the camera could not capture it all at once. The organism spiraled through the water in a slow, luminous coil, extending outward beyond the frame again and again as the vehicle continued filming. When researchers later reconstructed the full shape from the footage, the animal measured roughly 47 meters in length, longer than a blue whale, longer than any known animal reliably measured in the fossil record. Yet despite its scale, the creature moved with the softness of drifting silk. It was a siphonophore. At first glance, siphonophores resemble enormous jellyfish chains suspended through open water, but the comparison hides something stranger. A siphonophore is not a single animal in the ordinary sense. It is a colony composed of countless genetically identical units called zooids, each physically connected to the others and specialized for a single task. Some zooids propel the colony through the water. Others capture prey. Others reproduce or defend the body from predators. None can survive independently. Together, they form an integrated living structure, behaving as though it were one continuous organism. This arrangement has almost no equivalent elsewhere in the animal kingdom. The colony possesses no central brain directing the whole in the way vertebrate bodies coordinate themselves. Instead, function emerges collectively through the connected specialization of hundreds or even thousands of individual parts. The result resembles a city composed entirely of cloned bodies, each born already assigned to a permanent role. Siphonophores belong to the phylum Cnidaria, sharing ancient ancestry with jellyfish, corals, and sea anemones. Like their relatives, they possess stinging cells capable of injecting toxins into prey. Yet their colonial organization transformed those ancestral structures into something uniquely adapted for life in the open ocean. Instead of waiting attached to rocks or drifting as solitary bells, siphonophores extend themselves through enormous volumes of water like living fishing systems suspended in darkness. Their hunting strategy depends almost entirely on invisibility. Long curtains of tentacles trail behind the colony, armed with thousands of microscopic nematocysts capable of stunning small fish and crustaceans on contact. The prey often never perceives danger before touching the suspended threads. In deep water, where visibility is limited and movement expensive, the siphonophore allows the ocean itself to deliver food directly into its grasp. Most of the body is gelatinous tissue composed overwhelmingly of water. This softness makes siphonophores extraordinarily fragile. For decades, much of what scientists knew about them came from damaged fragments hauled upward in trawl nets. Conventional sampling methods tore the colonies apart before they could ever be observed intact, destroying their true shapes and sizes during collection. Only with the development of remotely operated vehicles capable of filming delicate organisms undisturbed in their natural environment did the scale of siphonophore life begin to emerge clearly. Some species carry another adaptation threaded along the colony. Coordinated bioluminescent organs can activate almost simultaneously, sending waves of blue light pulsing across the entire length of the organism in fractions of a second. A disturbance at one end becomes illumination, spreading through dozens of meters of living tissue, rippling outward through the dark water like electrical current moving through translucent nerves. Fragments of siphonophores have been recovered from the waters surrounding Point Nemo in deep trawl samples, evidence that these colonial animals drift through the remote Pacific Gyre as well. Yet intact individuals at their true scale have never been formally documented there. The isolation of the region leaves much of its pelagic ecosystem observed only in pieces, brief glimpses brought upward from depths where cameras rarely descend and fragile organisms dissolve before reaching the surface. And somewhere within those immense open waters, beyond the narrow paths traced by research vessels, entire colonies may still be extending silently through the mesopelagic dark, bodies longer than whales drifting unnoticed beneath one of the emptiest places on Earth. In the austral summer of the year 1997, somewhere within a network of listening stations spread across the Pacific Ocean, analysts monitoring underwater acoustics encountered a sound that did not resemble anything already cataloged in their recordings. The hydrophones had originally been installed decades earlier during the Cold War, designed to detect distant submarine movements through the ocean basin. By the late 20th century, the same instruments had become valuable scientific tools, continuously recording the shifting acoustic life of the sea itself, from earthquakes to whales to collapsing ice. Then the signal arrived. It lasted for roughly 1 minute. The sound was powerful enough to appear almost simultaneously on hydrophone stations separated by thousands of kilometers, moving through the Pacific with extraordinary clarity. Its amplitude ranked among the strongest acoustic events ever captured by the network. The analysts assigned it a simple, informal name, the Bloop, partly because no established scientific category seemed able to contain it. Triangulation placed the approximate origin near the remote waters surrounding Point Nemo. In another region of the ocean, the sound might have faded rapidly into the surrounding water. Here, however, the Pacific possessed a structure uniquely suited for carrying acoustics across immense distances. Far below the surface lies a layer known as the sound fixing and ranging channel, usually shortened to the SOFAR channel. At depths of roughly 600 to 900 meters, temperature, salinity, and pressure combine in a way that bends sound waves back inward whenever they attempt to escape upward or downward. Instead of dispersing through the ocean, acoustic energy becomes trapped within the layer and guided horizontally across enormous distances with surprisingly little loss of strength. The sea itself forms a natural waveguide extending through entire ocean basins. Blue whales use this channel constantly. Their low-frequency vocalizations travel across thousands of kilometers of open water, allowing communication between animals separated by distances no terrestrial sound could realistically cross. Submarine sonar systems exploit the same physics. So did the Bloop. Once the sound entered the SOFAR channel, it propagated through the Pacific with unusual efficiency, arriving at distant hydrophones still recognizable and intensely loud. What unsettled researchers initially was not merely the strength of the signal, but its character. Portions of the frequency profile resembled biological acoustics, containing rising and falling structures superficially similar to sounds produced by living organisms, yet the scale exceeded anything known. No documented whale, fish, or marine animal could generate such amplitude. The ocean held large creatures, but nothing approaching the necessary size or physiology required to create the recording captured by the hydrophone network. For years, the sound remained officially unexplained. Speculation accumulated gradually around it, spreading outward from scientific circles into documentaries, books, and early internet discussions. Some proposed volcanic activity or underwater landslides. Others Imagined classified military technology. The most persistent theories involved unknown organisms inhabiting the remote Pacific depths near Point Nemo itself, enormous biological entities hidden within regions of the ocean rarely visited by humans. The mystery persisted for approximately 15 years. Then, in the year 2012, researchers from the National Oceanic and Atmospheric Administration published a resolution based on improved analysis of polar acoustic data. The bloop had originated not from an animal, but from Antarctic ice. Large masses of ice shelf fracturing and shifting against one another generated low-frequency acoustic events known as icequakes. Sounds capable of entering the SOFAR channel and traveling extraordinary distances through the ocean. At the time of the original recording, the acoustic signatures produced by large Antarctic ice movements had not yet been fully documented, leaving the signal without a recognized comparison. The explanation removed the unknown creature from the story, but it left something else in its place. Across the southern edge of the Pacific, the Antarctic continent had fractured somewhere beyond the horizon, and the sound of that slow geological movement traveled invisibly through the deep ocean until it reached the loneliest waters on Earth. The hydrophones near Point Nemo had not recorded the voice of a hidden animal. They had recorded a continent breaking apart in darkness, its movement carried across the Pacific by the physics of the sea itself. Far below the migrating fish and drifting siphonophores, where the water presses inward with a force difficult for surface life to imagine, a small octopus moves slowly above the seafloor by flapping a pair of soft fins shaped vaguely like ears. The motion is unhurried and almost delicate, more like floating than swimming, as though the animal were gliding through the deep Pacific rather than pushing against it. Researchers who encounter these octopuses through submersible cameras often speak about them with unusual tenderness, perhaps because so little in the abyss appears gentle at first glance. The animal belongs to the genus Grimpoteuthis, commonly known as the Dumbo octopus. Unlike most octopuses familiar to human observation, it inhabits some of the deepest known regions of the ocean. Confirmed sightings extend beyond 7,000 meters beneath the surface, and in the year 2020, a specimen filmed within the Java Trench at nearly 6,957 meters became the deepest, reliably documented octopus observation ever recorded. At those depths, pressure exceeds hundreds of atmospheres. Every square inch of the animal's body exists beneath forces approaching 10,000 pounds, yet the Dumbo octopus moves through this environment with apparent ease because its anatomy contains almost nothing for the pressure to collapse. There are no internal air spaces, no rigid cavities filled with gas. Its tissues remain soft, gelatinous, and flexible, shaped by an environment where compression is permanent and unavoidable. Like many deep-sea organisms, the Dumbo octopus has abandoned structures useful only in the upper ocean. Most octopuses defend themselves by ejecting dark clouds of ink into the surrounding water, creating confusion while escaping predators. In the abyssal dark, however, no sunlight exists to silhouette an ink cloud against the water. Evolution gradually removed the organ altogether. The Dumbo octopus possesses no ink sac because the surrounding darkness already conceals it completely. Its skin still contains chromatophores, the pigment cells responsible for the dramatic color changes seen in shallow water octopuses near coral reefs and coastlines. Yet in the lightless deep sea, visual color displays serve little purpose. Instead, communication and concealment shift toward texture and posture. The animal alters the shape of its body and arms rather than its coloration becoming smooth or folded depending on movement and circumstance. Its blood carries hemocyanin, the copper-based oxygen-transporting molecule shared by many cephalopods, but in Dumbo octopuses, the chemistry functions particularly efficiently in cold, low-oxygen water. Near freezing temperatures that would slow or destabilize many biological systems become normal operating conditions for its metabolism. The animal is not merely surviving the cold of the abyss. Its entire physiology has become dependent upon it. Food arrives unpredictably at such depths, and the Dumbo octopus reflects that instability in its reproductive strategy. Females carry eggs at multiple developmental stages simultaneously, rather than producing a single synchronized brood. This allows eggs to be deposited gradually over time whenever conditions appear favorable. In an environment where meals may be separated by long intervals and seasonal patterns become faint or irrelevant, continuous reproductive flexibility becomes more reliable than concentrating all investment into one brief cycle. The octopus itself feeds quietly along or slightly above the seafloor. Small crustaceans, polychaete worms, and buried bivalves become prey when detected. Rather than tearing food apart, the Dumbo octopus engulfs organisms whole, drawing them inward through a beak adapted for swallowing comparatively small animals intact. In the broader South Pacific, species of Dumbo octopus have been documented in deep waters adjacent to the Point Nemo region. The abyssal plains and trenches surrounding the gyre provide precisely the conditions these cephalopods evolved to inhabit: near freezing temperatures, immense pressure, scarce prey, and perpetual darkness. There, beyond the reach of sunlight and storms, the soft-finned octopuses continue drifting through the deep Pacific floor, with movements so calm they seem almost detached from the violence of the environment surrounding them. Beneath stones in gardens and forests, small gray woodlice move quietly through damp soil and fallen leaves, armored bodies curling inward when disturbed. They are so familiar and so ordinary that it becomes easy to forget they belong to a much older lineage stretching far beyond the surface world. Deep beneath the Pacific, on abyssal plains where sunlight has never reached, close relatives of those tiny terrestrial crustaceans still roam the seafloor in forms enlarged to astonishing proportions. These are the giant isopods of the genus Bathynomus, scavengers adapted for life in the deep ocean where food arrives rarely and unpredictably. Most species measure somewhere between 14 and 50 centimeters in length, though some individuals grow considerably larger. The largest reliably documented specimen, collected from the Gulf of Mexico, reached roughly 76 centimeters and weighed nearly 1.7 kilograms. Suspended in darkness on the sea floor, such an animal resembles an ancient armored machine more than anything commonly associated with crustaceans. Its body is protected by overlapping calcified plates fitted together in articulated segments. The exoskeleton serves several purposes at once. It provides defense against competing scavengers gathering around carcasses, stabilizes the body under immense surrounding pressure, and creates a rigid framework allowing movement across soft abyssal sediment. Each segment flexes slightly against the next, giving the isopod enough mobility to crawl steadily across the seafloor while remaining heavily armored. The deep Pacific does not offer reliable meals. Weeks, months, or even longer periods can pass without substantial food reaching the abyssal plain. Giant isopods survive this uncertainty by reducing their metabolism to extraordinary levels. In captivity, some individuals have endured more than 4 years without feeding, remaining alive through long intervals of near stillness. Their physiology appears built not for constant consumption, but for waiting, conserving energy until a rare event interrupts the emptiness of the seafloor. When food finally arrives, the waiting ends quickly. A dead whale descending from the upper ocean becomes an immense concentration of organic matter in an otherwise sparse environment. Large fish carcasses, sharks, and other sinking animals create similar opportunities on a smaller scale. Giant isopods detect these falls through chemical traces drifting through the water and gather around them in groups, moving methodically across exposed tissue. Their feeding lacks urgency despite the rarity of the meal. They consume steadily, protected by armored bodies while competing scavengers crowd nearby in the dark. Their eyes remain among the most distinctive structures on the animal. Each compound eye contains thousands of reflective optical facets capable of amplifying faint available light. The reflective surfaces resemble those seen in nocturnal surface animals, such as cats, suggesting sensitivity to dim bioluminescent flashes and weak environmental illumination within the abyss. Even in regions approaching total darkness, the giant isopod may still perceive enough visual information to navigate toward movement and food. In evolutionary terms, these crustaceans are remarkably ancient. Their overall body structure has remained functionally stable for more than 160 million years. Creatures closely resembling modern giant isopods moved across Jurassic seafloors, while dinosaurs still dominated the continents above. The pressures shaping their existence changed so slowly that the design required little revision. Armor, patience, chemical detection, and metabolic endurance remained effective solutions across geological time. Species of deep-sea isopods have been collected from South Pacific benthic surveys in waters surrounding the Point Nemo region. The abyssal sediments there provide the same combination of cold temperature, high pressure, and sparse nutritional opportunity that shaped their physiology elsewhere across the deep ocean. On those remote plains beneath the gyre, giant isopods continue their slow movements across the seafloor, part scavenger and part living fossil, carrying a body plan so old that entire mountain ranges, oceans, and civilizations have appeared and vanished, while their lineage remained fundamentally unchanged. In the deep Pacific, time moves differently around such creatures. They persist through scarcity with extraordinary patience, waiting quietly in the darkness for the next distant body to descend from the world far above them. Long after their missions end, some spacecraft return to Earth not toward deserts, runways, or oceans crowded with ships, but toward a remote section of the South Pacific where almost no human presence exists at all. Guidance systems steer them deliberately toward the waters surrounding Point Nemo, allowing the remains of orbital machines to disappear into one of the most isolated environments on the planet. Since the 1970s, space agencies have relied on this region as a controlled graveyard for objects no longer meant to remain in orbit. The reasoning is simple. Re-entering spacecraft break apart unpredictably as they descend through the atmosphere, and surviving debris can travel across enormous distances before reaching the surface. By directing those descents toward the loneliest ocean on Earth, engineers minimize the chance of fragments reaching populated coastlines or major shipping routes. Over time, the remote Pacific surrounding Point Nemo accumulated the remains of more than 263 spacecraft and orbital structures. Russian Progress cargo vessels, European resupply craft, Japanese transfer vehicles, discarded rocket stages, and sections of the Mir space station all descended there. When Mir re-entered Earth's atmosphere in the year 2001, the station fragmented across hundreds of kilometers of open ocean, scattering surviving components downward through the Pacific sky before they vanished into the sea below. The descent itself is violent. Spacecraft returning from orbit strike the upper atmosphere at velocities exceeding 7 kilometers per second. Friction compresses surrounding air into plasma heated beyond 1,600 degrees Celsius. Much of the structure vaporizes or burns apart during re-entry, leaving only the densest components intact. Fuel tanks, engine bells, pressure vessels, and reinforced structural elements survive longest, continuing downward through smoke and incandescent debris before finally striking the ocean surface at tremendous speed. Those impacts do not pass silently into the sea. Shock waves propagate outward through the water column, recorded by the same hydrophone systems that once captured the Bloop. Each spacecraft entering the Pacific graveyard leaves behind an acoustic signature, one final mechanical sound added briefly to the ocean's ongoing record before the debris begins its descent toward the abyssal plain. The fragments sink slowly through nearly 4 kilometers of water before reaching the seafloor beneath Point Nemo. There, they encounter an environment unexpectedly shaped by absence. The abyssal plain consists largely of soft sediment, extending outward in broad, uninterrupted expanses. Hard surfaces suitable for attachment are uncommon. For many deep-sea organisms, solid substrate represents a valuable ecological resource precisely because it is so rare. When artificial structures appear in the deep ocean, life begins settling onto them with surprising speed. Studies of submerged wrecks and experimental seafloor installations show that bacteria, sessile invertebrates, crustaceans, and tube-dwelling organisms colonize exposed hard surfaces within only a few years under suitable conditions. The arriving organisms alter local chemistry, trap drifting particles, and gradually create small biological communities around material that once traveled through orbit above Earth. The surviving debris from Mir has rested on the seafloor for more than 2 decades now. During that time, the metal structures almost certainly accumulated biological growth within the darkness beneath the gyre. Chemosynthetic bacteria may coat exposed surfaces. Small invertebrates may cluster around edges and cavities where currents slow slightly against the wreckage. Crustaceans adapted to abyssal sediment likely move among the fragments, searching for organic material settling from above. Yet despite the unusual nature of the site, no crewed, submersible, or remotely operated vehicle has ever conducted a direct visual survey of the central debris fields. No camera has documented what now lives upon those scattered spacecraft remains. The Pacific graveyard remains largely unvisited, hidden beneath pressure, cold, and darkness at the bottom of one of the least accessible regions on Earth. And so the machines humanity once built to survive the vacuum of space now rest quietly on the abyssal floor beneath Point Nemo, gradually becoming part of a deep ocean ecosystem that never evolved with any expectation of encountering metal from orbit. In the stillness below the gyre, abandoned spacecraft and ancient marine life now share the same seafloor, connected by the slow, patient processes of the deep Pacific, far below the slow turning currents of the South Pacific, where food drifts downward so sparsely that entire stretches of seafloor may wait years between substantial meals. The death of a whale becomes something almost geological. A body that floated through the bright surface ocean for decades eventually begins its descent, slipping beneath the waves and falling through kilometers of cold water toward the abyss below. By the time it reaches the floor near Point Nemo, what arrives is not simply a carcass, but an immense concentration of energy entering one of the least nourished places on Earth. A blue whale can reach lengths of nearly 30 meters and masses approaching 200 metric tons. When such an animal settles onto the abyssal plain, the surrounding ecosystem changes almost immediately. In regions where the seafloor survives on the faint downward drift of organic particles, the sudden arrival of dense flesh, fat, collagen, and bone transforms the sediment around it into a temporary center of abundance. The event resembles a forest appearing suddenly in the middle of a desert plain, except the transformation unfolds in darkness beneath thousands of meters of water. The first arrivals are mobile scavengers, capable of detecting chemical traces, dispersing slowly through the deep ocean currents. Hagfish slip through openings in the soft tissue, knotting their bodies for leverage as they tear flesh free in strips. Sleeper sharks circle heavily through the dark, feeding in slow, deliberate motions. Giant isopods emerge from the sediment around the carcass and gather across its surface in clusters of armored bodies. In more productive oceans, this stage can reduce a whale almost entirely to bone within months. But near Point Nemo, where fewer large scavengers patrol the abyssal plain, the process likely stretches longer into the surrounding years. As the remaining tissue diminishes, a second community begins to emerge directly within the sediment around the skeleton itself. Polychaete worms spread through the surrounding mud. Dense bacterial mats bloom pale against the seafloor. Small crustaceans occupy cavities inside vertebrae and ribs. The chemistry of the sediment changes as decomposing organic material enriches an environment normally starved of nutrients. Organisms adapted for scarcity suddenly encounter concentrations of carbon and nitrogen rarely available in the interior of the gyre. Then the whale begins sustaining life in a completely different way. Deep within the bones, lipids remain trapped long after the flesh has vanished. Anaerobic bacteria slowly break these compounds apart, releasing hydrogen sulfide into the surrounding sediment. That sulfide becomes energy. Chemosynthetic bacteria flourish around the skeleton, drawing nourishment not from sunlight, but from chemistry itself, constructing an entirely new food web around the remains of a single animal. This sulfophilic stage can continue for decades. In large whale skeletons, the process may persist for as long as a century, long enough for generations of organisms to live and die around the same bones. A whale that once crossed entire oceans at the surface becomes a stable deep-sea habitat, enduring longer than many human institutions on land. Some organisms appear almost exclusively at these sites. Among the strangest is Ocedax, often called the zombie worm. It possesses no mouth and no digestive tract. Instead, root-like structures extend directly into whalebone, secreting acid that dissolves the surface and allows symbiotic bacteria within the worm's tissue to process the released nutrients. Entire colonies of these delicate organisms bloom from exposed skeletons, like pale underwater flowers anchored into ancient vertebrae. Researchers studying whale fall ecosystems in the Pacific have noticed something else as well. Many of the species living around whale carcasses share genetic relationships with organisms inhabiting hydrothermal vents and cold seeps. Whale falls may function as temporary bridges across the abyss, allowing vent-adapted species to disperse slowly between distant geological habitats separated by enormous stretches of seafloor. Near Point Nemo, whale falls are likely rare events. Migrating whales cross the gyre less frequently than richer ocean regions closer to continental margins. Yet that rarity only deepens their significance. In one of the most nutrient-poor places on Earth, the descent of a single whale can nourish entire communities for generations, transforming an empty stretch of abyssal plain into a living oasis beneath the cold, permanent dark. For most of human history, life seemed inseparable from sunlight. Forests, grasslands, coral reefs, migrating animals, even the oxygen in the atmosphere all traced themselves back to the same distant source above the planet. Energy moved outward from the sun through leaves and algae and plankton, passing from one body into another in an unbroken chain. The deep ocean appeared excluded from that system, only temporarily, surviving on fragments drifting downward from the illuminated world overhead. Then, in the year 1977, a research descent into the Pacific altered that understanding permanently. The submersible Alvin descended toward the Galapagos Rift, carrying scientists into darkness far below the reach of sunlight. There, on the seafloor surrounding fractures in Earth's crust, the lights of the submersible revealed something no one expected to find. Towering tube worms rose more than 2 meters above the rock. Clams larger than dinner plates clustered across mineral deposits. Dense white bacterial mats covered the ground in broad, irregular sheets. Crabs and shrimp crowded together in such numbers that their bodies overlapped one another around the openings in the crust. Superheated water, rich in dissolved minerals, poured continuously from the seafloor. No sunlight had ever reached this depth. Nothing in that ecosystem relied on photosynthesis. Yet the community surrounding those vents was thriving with extraordinary density and complexity. The source of energy was chemistry itself. Certain bacteria and archaea possess the ability to extract energy from inorganic compounds such as hydrogen, sulfide, methane, and ammonia. Rather than capturing photons from sunlight, they harvest chemical energy released through reactions involving these substances, using it to build organic matter. In the same broad way, plants use sunlight at the surface. This process became known as chemosynthesis, and its discovery transformed biology's understanding of what environments could sustain life. Among the most remarkable inhabitants of hydrothermal vents are the giant tube worms of the genus Riftia pachyptilla. These animals possess no mouth, stomach, or digestive tract. Their bodies, instead, contain a specialized internal organ called a trophosome, packed densely with chemosynthetic bacteria. The worm absorbs hydrogen sulfide and oxygen from vent water through its tissues and delivers those compounds directly to its bacterial partners. In return, the bacteria synthesize the nutrients, sustaining the worm itself. Animal and microbe become inseparable parts of a single metabolic system, each surviving entirely through the chemistry emerging from Earth's crust. Similar ecosystems form in places known as cold seeps, where methane and sulfide-rich fluids escape slowly through sediment without the extreme heat associated with hydrothermal vents. Around these seeps, bacterial communities support clams, worms, crustaceans, and other organisms adapted to chemical energy rather than sunlight. Some cold seep ecosystems persist for thousands of years, remaining stable as long as the underlying chemistry continues flowing upward from below the seafloor. Whether such systems exist directly beneath Point Nemo remains unresolved. The abyssal plain surrounding those coordinates is among the least surveyed regions on Earth. Vast sections of the seafloor there have never been visually examined by submersible or remotely operated vehicle. If hydrothermal vents or cold seeps do occur beneath the gyre, they may have remained isolated from other vent systems across geological timescales, measured in millions of years. That isolation carries profound biological consequences. Vent communities separated for immense periods gradually diverge through evolution, adapting to local chemistry, pressure, and geology. Beneath Point Nemo, undiscovered chemosynthetic ecosystems could potentially contain species existing nowhere else on the planet, organisms shaped entirely by conditions hidden beneath the South Pacific abyss. The discovery of chemosynthesis altered more than marine biology. It changed the boundaries surrounding the idea of habitability itself. Life no longer appeared dependent upon sunlight, warmth, or proximity to continents. It could emerge wherever liquid water, suitable chemistry, and enough time existed together. Far beneath the nutrient-starved waters of Point Nemo, where darkness remains complete and the surface world feels impossibly distant, that realization lingers quietly through the cold Pacific depths, expanding the meaning of what it means for a world to be alive. In the deep Pacific, bodies begin to change shape in ways that would appear impossible near the surface. Features that seem grotesque or exaggerated from a human perspective are often the result of extreme efficiency. Solutions refined slowly in darkness where food is scarce, visibility is almost non-existent, and encounters between animals may be separated by vast distances and long spans of time. Down there, evolution does not favor elegance in the familiar sense. It favors survival under conditions so different from the surface world that the resulting creatures often seem almost detached from ordinary biology. Among the most unusual are the anglerfish, a collection of deep-sea species belonging to the superorder Serratioidae. Females drift through the dark, carrying a luminous structure extending from the forehead on a modified dorsal spine. At its tip sits a fleshy bulb called the esca, inhabited by symbiotic bacteria that generate cold blue light. Small fish and crustaceans approach the glow through instinct or curiosity, unable to distinguish it from other bioluminescent signals surrounding them in the water column. The anglerfish remains motionless until prey drifts close enough for a sudden strike. Its jaws and stomach possess remarkable elasticity. Meals in the abyss may arrive only rarely, and prey cannot be wasted because it happens to exceed the predator's normal proportions. Female anglerfish can swallow animals nearly twice their own size, their bodies expanding to accommodate opportunities that may not come again for weeks or months. The males live under entirely different biological rules. Tiny compared to the females, they devote most of their existence to locating a mate within the enormous darkness of the deep ocean. Guided primarily by scent, the male eventually encounters a female and bites into her body. Then something extraordinary begins. Tissue fuses gradually between them. Blood vessels connect. The male's organs degenerate over time until little remains except reproductive tissue supplied directly by the female's circulatory system. Some females carry multiple fused males simultaneously, permanent biological attachments drifting with them through the abyss. Elsewhere in the water column, another predator moves with a different strategy entirely. The viperfish, Choliotis sloani, possesses teeth so oversized that its jaws cannot fully close around them. The fangs curve backward toward the eyes like polished needles, evolved not for chewing, but for immediate capture. In near total darkness, precise pursuit becomes difficult. The viperfish instead relies on ambush and speed, impaling fast-moving prey before it can escape. Its body remains slender and dark, interrupted only by occasional flashes from bioluminescent organs arranged along its sides. Then there is the barrel-eye fish, Macropinna microstoma, whose anatomy remained misunderstood for decades because damaged specimens collapsed before reaching the surface intact. Inside a transparent fluid-filled dome atop its head sit tubular eyes capable of rotating within the skull. Most of the time, the eyes point upward, scanning faint silhouettes drifting above against the dim traces of distant light from the surface. When prey moves directly ahead, the eyes rotate forward. The transparent shield protecting them was so unexpected that even after the species became known to science, its true appearance was not fully documented until the early years of the 21st century. Deeper still live the snailfish, soft-bodied vertebrates, occupying some of the most pressurized environments ever known to support fish life. Specimens have been recorded below 8,000 meters within Pacific trenches, where pressure would collapse most surface-adapted anatomy instantly. Their bodies contain no rigid structures vulnerable to implosion. Specialized lipids within their cellular membranes remain flexible under immense pressure and near freezing temperatures, preserving the chemistry necessary for life in conditions once assumed biologically impossible. Together, these animals reveal something essential about the deep ocean. Isolation, darkness, and scarcity do not simplify life. They reshape it. Over millions of years beneath the South Pacific, evolution has produced organisms whose forms appear almost unreal from the perspective of the sunlit world above. Yet every spine, lure, transparent surface, and flexible tissue exists for a reason written slowly by the conditions of the abyss itself. At the bottom of the South Pacific, beneath nearly 4 kilometers of water and far below the drifting animals of the open ocean, the seafloor becomes astonishingly flat. The abyssal plain surrounding Point Nemo stretches outward for thousands of kilometers, with such subtle changes in elevation that entire regions vary only by a few meters across distances larger than many countries. Mountains, trenches, and volcanic ridges exist elsewhere beneath the Pacific, but here they lie buried under a slow accumulation of sediment that has softened the landscape into something vast and nearly featureless. This plain was not shaped quickly. It formed through patience measured in geological time. Tiny particles descending through the water column settled layer upon layer across the ancient seafloor, gradually covering older volcanic structures beneath blankets of biological remains, mineral dust, and microscopic debris. Over millions of years, irregular topography disappeared under this continual downward drift until the abyss became smooth enough to resemble an underwater desert extending beyond sight. The dominant sediment here is red clay, one of the slowest accumulating materials in the ocean. In some regions of the abyssal plain, only a millimeter or two may settle over an entire 1,000 years. A thin layer disturbed by a passing organism today could contain particles older than human civilization itself. Just centimeters below the surface, the sediment may preserve material deposited tens of millions of years ago, resting quietly beneath the cold Pacific in nearly unchanged conditions. Mixed invisibly into that clay are particles that did not originate on Earth at all. Micrometeorites enter the atmosphere continually, many burning apart before reaching the surface. But some survive as microscopic fragments known as cosmic spherules. These tiny grains descend slowly through the ocean after falling from space, drifting downward through kilometers of water before finally settling across the abyssal plain. The sediment beneath Point Nemo contains measurable traces of extraterrestrial material, a faint accumulation of matter that once traveled between planets before becoming part of the Pacific seafloor. Scattered across parts of the abyssal plain lie manganese nodules, dark rounded concretions rich in manganese, iron, nickel, cobalt, and copper. They resemble rough stones resting half buried in the sediment, though they grow so slowly that their formation approaches stillness. Layer after layer accumulates concentrically around a small central object, perhaps a shark tooth, a fragment of volcanic glass, or a piece of ancient bone. Over millions of years, the nodule enlarges by only a few millimeters, becoming a geological structure shaped by almost unimaginable patience. Even these stones become habitat. In a landscape dominated by soft sediment, any solid surface acquires ecological importance. Microbial communities spread across manganese nodules in thin living films. Small mobile organisms gather around them for shelter and attachment. What appears lifeless from a distance becomes, at close scale, a small island of activity rising gently above the plain. Beneath the upper clay layers, additional records accumulate. Radiolarian ooze forms from the silica skeletons of microscopic plankton drifting down from the upper ocean. These skeletal remains settle continuously through the water column and compress slowly into layered deposits, preserving changing ocean conditions across immense stretches of time. Temperature shifts, productivity changes, volcanic events, and chemical alterations in the Pacific become written quietly into the sediment beneath Point Nemo. Now another layer has joined that archive. Microplastic particles have been identified in abyssal sediments across some of the most remote ocean basins on Earth. Fragments smaller than grains of sand descend through the water, attached to marine snow and organic debris, eventually settling onto the deep sea floor alongside clay, biological remains, and cosmic dust. The sediment beneath Point Nemo almost certainly contains this material as well, forming a thin modern horizon marking the rise of industrial civilization during the 20th century. So the abyssal plain beneath the loneliest ocean on Earth becomes something more than empty seafloor. It is an archive assembled grain by grain across deep time, recording asteroid dust, extinct organisms, drifting continents, ancient oceans, and now traces of humanity itself, all resting together beneath the silent Pacific dark. For a long time, the deep ocean seemed populated mainly by animals sturdy enough to survive capture. Nets dragged upward from the abyss returned fish with oversized jaws, armored crustaceans, squid with enormous eyes, and other creatures capable of enduring at least part of the violent ascent toward the surface. Marine biology built its early understanding of the deep water column around what could be physically collected and preserved. Anything too delicate to survive the process often disappeared before researchers realized it had been there at all. The problem was not absence, it was fragility. Gelatinous animals, including jellyfish, salps, siphonophores, and pyrosomes, possess bodies composed mostly of water, with tissues so delicate that traditional trawl nets frequently reduce them to transparent fragments and mucus before they reached the deck of a ship. For decades, they appeared to be minor components of the ecosystem, simply because the primary tools used to study the deep sea destroyed them almost completely. Only with the arrival of remotely operated vehicles and deep-sea camera systems during the late 20th and early 21st centuries did the actual scale of their presence begin to emerge. Illuminated gently in their natural environment rather than crushed during collection, enormous populations of gelatinous organisms became visible drifting through the darkness. In many regions of the open ocean, they were not rare at all. They constituted the majority of visible animal biomass in the water column, entire drifting ecosystems that had remained largely invisible to science because of the methods used to search for them. Among the most abundant are salps, transparent barrel-shaped animals that move slowly by pumping water through their bodies while filtering microscopic food particles from the surrounding sea. Under favorable conditions, salps reproduce both sexually and asexually, generating long chains of identical individuals connected together in drifting colonies. Some chains stretch for astonishing distances through the water. As salps feed, they produce dense pellets of compressed organic material that sink rapidly toward the abyssal plain, transporting carbon from surface waters into the deep ocean with extraordinary efficiency. Pyrosomes move differently. These colonial animals form hollow cylinders composed of countless tiny zooids embedded together into a shared gelatinous structure. Each zooid draws water inward while filtering food, then expels that water toward the center of the colony, generating propulsion through collective action. Some pyrosomes reach lengths approaching 18 meters. At night or in deep water, their entire surface emits a slow, pulsing blue-green glow. Researchers encountering large colonies drifting silently through darkness have often described the sight as strangely unreal, like observing living constellations suspended beneath the sea. Comb jellies, or siphonophores, create another kind of display altogether. Their bodies do not produce bioluminescence in the same chemical way many deep-sea organisms do. Instead, rows of tiny beating cilia running along their bodies refract and scatter light into shifting rainbow patterns when illuminated by submersible lamps. The colors ripple across their transparent tissues in moving bands impossible to perceive without artificial light reaching them from outside. Even familiar jellyfish adopt unusual strategies in the abyss. Atolla wiveli, a deep-sea species drifting through midwater darkness, produces rotating rings of blue light when attacked. Rather than functioning as camouflage or escape, the flashing display serves as an alarm signal intended to attract larger predators toward the attacker itself. In the deep Pacific, light becomes both communication and weapon, altering the behavior of surrounding animals through brief pulses in the dark. Within the waters surrounding Point Nemo, gelatinous life likely dominates even more completely than in richer ocean regions closer to continents. Fish and crustacean populations thin considerably beneath the nutrient-starved gyre, yet gelatinous organisms continue drifting through the water column in enormous numbers, sustained by remarkable efficiency and low energy requirements. So the loneliest ocean on Earth is not empty at all. It is filled with transparent colonies, drifting chains, pulsing cylinders, delicate combs, and living curtains of gelatinous tissue moving silently through the dark Pacific depths. For much of scientific history, they remained unseen not because they were rare, but because the deep ocean concealed them within bodies too fragile for human tools to hold together. Long before cameras reached these depths, the ocean had already been speaking. Every movement through water creates pressure waves. Every fracture in distant ice releases vibrations into the sea. Every hunting whale sends bursts of sound across entire basins. Around Point Nemo, where visual observation is rare and the nearest human presence may be thousands of kilometers away, acoustics become the primary record of life and motion. The water itself functions as a vast transmitting medium, carrying information through darkness with remarkable efficiency. Much of this transmission occurs through the SOFAR channel, a horizontal layer formed where pressure, temperature, and salinity combine in precise balance. Sounds entering this layer bend back inward instead of dispersing upward toward the surface or downward into the abyss. Once captured there, acoustic waves can travel extraordinary distances while losing very little energy. A call produced in one part of the Pacific may continue moving silently through the ocean for thousands of kilometers before fading. Among the most powerful biological sources within this underwater soundscape are sperm whales. Deep beneath the surface, these animals hunt colossal squid and other prey using bursts of echolocation clicks that rank among the loudest sounds produced by any living organism. The clicks originate inside the spermaceti organ, an immense oil-filled structure occupying much of the whale's head. Layers of specialized fatty tissue focus the sound forward into a concentrated beam, transforming the whale into a living acoustic instrument. At the source, these clicks can exceed 230 decibels. In human experience, almost nothing approaches such intensity except explosions. Yet sperm whales release these pulses repeatedly while descending through darkness, then interpret the returning echoes to construct detailed acoustic images of their surroundings. A squid drifting hundreds of meters away becomes visible through reflected sound alone. Shape, density, distance, and movement emerge from the echoes returning through black water where no sunlight has existed for kilometers above. Hydrophone arrays operating across the South Pacific have detected sperm whale clicks near the Point Nemo region, even when no surface sightings occurred. Their bodies remained unseen, but their presence moved through the water unmistakably, recorded by instruments listening continuously beneath the Pacific. Blue whales speak differently. Their calls occur near the lower threshold of human hearing, around 20 Hz, deep resonant tones capable of crossing entire ocean basins through the same acoustic pathways. These vocalizations travel immense distances because low-frequency sound loses energy slowly underwater. A single whale may be communicating with another hundreds or even thousands of kilometers away, the ocean carrying its voice across darkness and open water with almost no obstruction. Closer to the mesopelagic depths, countless smaller fish participate in their own continuous acoustic exchanges. Many species generate drumming, clicking, or grunting sounds using muscles vibrating against their swim bladders, transforming those internal gas-filled chambers into resonating instruments. In darkness, where visual displays become nearly useless, sound provides identity, territory, and location. The deep sea contains an immense biological conversation, still only partially cataloged by science. Even tiny crustaceans contribute to this underwater chorus. Snapping shrimp close their specialized claws with such speed that collapsing cavitation bubbles produce shockwaves powerful enough to stun prey. Individually, the sound is sharp and brief. Collectively, vast colonies generate a continuous broadband crackling that submarine operators have long recognized as one of the dominant natural noises in many marine environments. Since the hydrophone network first detected the sound, later named the Bloop, instruments have continued listening to the waters surrounding Point Nemo without interruption. Year after year, they preserve an acoustic archive of whale migrations, shifting ice, storms, distant earthquakes, ship passages, and biological activity moving unseen through the Pacific darkness. So even in the most isolated waters on Earth, the ocean is never truly still. Beneath the silence perceived from above exists an immense and ongoing exchange of vibrations, pulses, echoes, and calls, a hidden portrait of life and motion carried endlessly through the deep waters surrounding Point Nemo. Far beneath the drifting animals of the water column, beneath the sediment where whale bones slowly dissolve and metallic nodules gather layers across geological ages, the seafloor continues downward into compressed darkness. There, under the abyssal plain surrounding Point Nemo, life persists in forms so slow and ancient that ordinary ideas of survival begin to lose meaning. No movement is visible. No predator hunts. No current stirs these buried layers. Yet, within the compacted chemistry of deep sediment, living cells continue their quiet existence. These organisms belong primarily to the domain Archaea, one of the three great branches of life, alongside bacteria and nucleated organisms. Their ancestry reaches backward toward the earliest periods of Earth's history, long before forests, animals, or oxygen-rich skies transformed the planet. The ancestors of modern Archaea may have emerged when Earth's oceans were warmer, volcanic gases dominated the atmosphere, and multicellular life had not yet appeared. In many ways, they remain connected to those ancient conditions more closely than almost any visible organism alive today. Deep sediment cores recovered from abyssal regions around the world have revealed archaeal communities living astonishing distances beneath the seafloor. Some remain metabolically active more than 2,500 meters below the ocean floor itself, embedded within ancient rock and compressed sediment where pressure and isolation become almost unimaginable. Above them rests not only the entire ocean, but also millions of years of accumulated biological remains, mineral dust, volcanic ash, and microscopic debris from space. The energy available to these organisms is almost non-existent by surface standards. Tiny traces of organic carbon descend gradually through the water column over immense spans of time, becoming buried layer after layer beneath new sediment. What finally reaches the Archaea below is chemically exhausted material stripped of nearly all accessible energy. Yet even there, life continues extracting enough from the environment to persist. Some archaeal populations divide so slowly that a single cellular generation may require approximately 10,000 years. One cell becoming two spans a period longer than the entirety of recorded human civilization. During the interval required for a single division, empires rise and vanish, coastlines shift, languages disappear, and entire species emerge into history before fading again. The metabolism of these organisms operates at the absolute lower boundary of what biology appears capable of sustaining. And still, they are not dormant. Chemical analysis shows active metabolism continuing within their cells. Molecules move, energy transfers occur. Genetic material repairs itself slowly against time and pressure. The distinction between living biology and surrounding geology becomes extraordinarily thin, yet it remains real. These archaea exist in a state where life approaches stillness without ever completely reaching it. Marine Group 1, archaea, dominate large portions of the deep ocean water column as well, particularly in nutrient-poor regions like the South Pacific Gyre. Rather than depending on sunlight, they obtain energy by oxidizing ammonia, quietly transforming nitrogen compounds through processes that influence ocean chemistry across the planet. Invisible to human senses, they participate continuously in cycles regulating the biological balance of Earth itself. In several abyssal sediment studies, the carbon consumed by buried microbial communities has been radiocarbon dated to thousands of years in age before metabolism even began. The material entering their cells may have fallen through ancient oceans, while the first cities of Mesopotamia stood beside newly irrigated rivers. Human history, compressed into archaeology and memory above, arrives below only as faint chemical residue drifting downward through darkness. Beneath Point Nemo, these archaea are likely the oldest uninterrupted inhabitants of the region. They existed before the gyre stabilized its slow rotation across the Pacific. They existed before human navigation crossed these waters, before coordinates were calculated, before names were assigned to the emptiness above them. Long after surface civilizations disappear and oceans continue their patient circulation beneath distant stars, these buried communities may still remain in the sediment, dividing once again across another 10,000 years of darkness. Isolation at the surface can create the illusion of separation below, as though the immense emptiness surrounding Point Nemo extends downward through every layer of the Pacific unchanged. Yet the deep ocean follows pathways invisible from above. Beneath the stillness of the gyre, water continues moving across the planet through currents so slow and cold that their journeys unfold across human centuries. Through these hidden circulations, life reached even this remote abyss. One of the most important of these pathways begins beside Antarctica. Along the frozen continental margins surrounding the southern continent, seawater cools to near freezing temperatures, while sea ice formation leaves behind concentrated salt. The remaining water becomes extraordinarily dense, heavier than the layers above it. Eventually, it sinks and spreads outward along the seafloor as Antarctic bottom water, one of the coldest and densest water masses anywhere on Earth. This bottom water does not remain near Antarctica. It advances gradually northward, beneath the Pacific, Indian, and Atlantic Oceans, flowing through abyssal basins like an immense submerged river. Near the seafloor beneath Point Nemo, this current continues its passage through darkness, carrying with it traces of distant regions, far beyond the gyre's isolated surface waters. Suspended within this moving water are bacterial cells, fungal spores, dissolved nutrients, microscopic organic particles, and the drifting larvae of deep-sea organisms. Chemical signatures from Antarctic sediments travel as well, mingling with the waters crossing the abyssal plain. The process is slow beyond ordinary intuition. Water beginning its descent near Antarctica may require decades or centuries to arrive beneath Point Nemo. The biological material traveling with it experiences a journey conducted entirely through cold darkness beneath 4 kilometers of ocean. Unlike the rapid migrations of surface animals, this dispersal unfolds almost invisibly. A single microbial cell may drift for generations before encountering sediment where conditions allow survival. Tiny larvae released from distant seafloor communities may travel extraordinary distances while suspended within bottom currents, settling eventually into unfamiliar habitats where only a few survive long enough to reproduce. Most vanish, some persist. Across geological spans, that becomes enough. Genetic studies from isolated abyssal environments reveal the consequences of this slow connectivity. Deep-sea microbial populations separated by enormous distances still share ancient relationships, evidence that bottom currents occasionally transport living founders between regions. Yet, the exchange occurs infrequently enough that evolution gradually pulls these populations apart over immense periods of time. Isolation remains incomplete, but it is strong enough for divergence to accumulate quietly across millions of years. In some abyssal sediments, microorganisms already display genetic patterns unlike those found elsewhere in sampled oceans. Beneath Point Nemo, where scientific surveys remain sparse and sediment cores are limited, entirely distinct microbial lineages may already exist undiscovered. Certain species may have diverged for such extraordinary lengths of time that no close relatives remain known anywhere else on Earth. The deep ocean allows this because time functions differently there. Surface ecosystems change rapidly beneath storms, seasons, migrations, and human activity. Abyssal environments evolve with immense slowness. Currents move gradually, temperatures remain stable, and biological turnover occurs across spans difficult for human minds to fully absorb. In that stability, Even rare events become powerful when repeated over geological ages. A single successful arrival every few thousand years may be sufficient to establish a lineage. A microscopic founder drifting unnoticed through Antarctic bottom water may eventually give rise to entire populations spread across sediment beneath the Pacific. Distance alone does not prevent colonization when the planet provides enough time for chance encounters to accumulate. So life reached Point Nemo not through abundance or easy access, but through persistence carried by the architecture of the ocean itself. Hidden beneath the gyre's apparent emptiness, cold bottom currents maintained faint connections between remote regions of Earth for millions of years. The pathways were narrow, the movements slow, and the journeys unimaginably long, yet they were enough. In the deep ocean, almost any barrier can eventually be crossed when water continues moving and time never truly ends. From the perspective of the surface world, Point Nemo appears almost impossibly detached. The nearest coasts lie thousands of kilometers away across uninterrupted Pacific water, beyond ordinary shipping routes and far outside the rhythms of daily human activity. Maps portray it as emptiness, a coordinate surrounded by distance in every direction. Yet, beneath the surface, isolation becomes more complicated. The deeper the descent continues, the more the boundaries begin to dissolve. Creatures living in these waters remain physically separated from continental shores by approximately 2,688 kilometers of ocean. No reef corridors connect them to shallow ecosystems. No drifting forests of kelp bridge the distance. Above them stretches one of the most nutrient-starved surface regions on Earth. And still, through other pathways invisible from above, they remain linked to environments across the entire Pacific Basin. Sound is one of those pathways. Within the Sofar Channel, whale calls, shifting ice, submarine earthquakes, and distant biological movements travel enormous distances through seawater with remarkable efficiency. A sperm whale hunting far from Point Nemo may send acoustic pulses that eventually pass through these waters hours later. Blue whale songs originating near Antarctica can continue propagating northward through the Pacific long after the animal itself has vanished beyond the horizon. Even here, at the loneliest coordinates on Earth's surface, the ocean continues, carrying echoes from distant places. Chemistry provides another connection. While the gyre isolates the surface from surrounding circulation, the abyss below belongs to a different system entirely. Antarctic bottom water continues its gradual movement through the deep Pacific, transporting dissolved minerals, microbial life, and ancient chemical signatures northward beneath the seafloor plain. Nutritionally, Point Nemo remains extraordinarily poor, receiving only sparse organic material from the depleted surface waters above. Yet, chemically, it remains connected to distant Antarctic margins through currents moving patiently across centuries. Even light, absent from the abyss for millions of years, reappears through biology itself. Many inhabitants of these depths generate bioluminescence with such precision that communication, camouflage, hunting, and defense all depend upon it. Specialized eyes evolve specifically for these wavelengths, detect flashes impossible for surface-adapted vision to perceive. In darkness, absolute by human standards, an entirely different visual world continues unfolding through pulses of cold blue and green light. Pressure creates another apparent contradiction. At depths beneath Point Nemo, the surrounding force would crush unprotected human bodies instantly and collapse ordinary structures engineered for the surface world. Yet, The organisms native to these depths experience no violence from the pressure surrounding them. Their tissues contain almost no compressible air spaces. Their cells exist in equilibrium with the immense force pressing inward from every direction. To them, the abyss is not crushing, it is simply normal. The same pattern extends through the entire deep ocean system. Surface geography that appears dominant on maps loses importance in abyssal environments. The gyre that isolates Point Nemo from surrounding waters near the surface becomes largely irrelevant several kilometers below. Different temperatures govern the abyss, different currents circulate there, and different ecological rules determine survival. Deep water communities are shaped less by latitude or coastline proximity than by enduring environmental conditions repeated throughout the planet's interior oceans. Cold, darkness, pressure, scarcity, and immense spans of time define these environments more strongly than any national boundary or geographic coordinate ever could. Organisms adapted to such conditions may appear in widely separated ocean basins because the deep sea itself remains fundamentally continuous. The abyss surrounding Point Nemo connects gradually and invisibly with trenches, plains, and deep currents extending across the entire planet. This is the quiet paradox at the center of Point Nemo. The surface above represents one of Earth's most isolated locations, yet the deep ocean beneath belongs to a connected planetary system operating beyond ordinary human perception. Water circulates between continents over centuries. Sound crosses basins without interruption. Microbial lineages disperse slowly through abyssal currents. The deep Pacific is not fragmented into separate worlds, but joined into one continuous realm of cold and darkness, extending beneath every ocean on Earth. Nothing human lives near Point Nemo. No cities stand along nearby coastlines, no rivers empty into these waters, and no permanent ships remain drifting above the abyssal plain. From the surface, the region appears detached from civilization almost completely. Yet fragments of human industry still arrive there, continuously, carried not by intention, but by the ordinary motion of the sea itself. Across the world's oceans, plastic breaks apart gradually beneath sunlight, salt, and mechanical stress from waves. Bottles become fragments, fragments become fibers, and fibers eventually become particles so small they disappear from ordinary sight. Microplastics, defined as pieces smaller than 5 millimeters, now circulate through nearly every marine environment studied by scientists, including the remote waters of the South Pacific Gyre surrounding Point Nemo. The gyre contributes directly to this accumulation. Surface currents rotating through the South Pacific gather floating material from distant coastlines and shipping routes, drawing debris slowly inward toward the gyre's center. The movement resembles a vast circular conveyor operating across thousands of kilometers, concentrating fragments that may have originated continents away. Some portions intersect with diffuse regions of floating debris, sometimes described collectively as the South Pacific Garbage Patch, though the reality is less like a visible island and more like an immense suspension of particles spread through open water. These plastics do not remain chemically inert while drifting through the ocean. Their surfaces absorb persistent organic pollutants already dissolved in seawater, including compounds such as polychlorinated biphenyls, degraded pesticide residues, and polycyclic aromatic hydrocarbons released through combustion and industrial processes. Concentrations on plastic surfaces can become far higher than in the surrounding water itself. Any organism swallowing the particle consumes not only the plastic, but also the chemical cargo attached to it. Microplastics have now been identified within copepods, mesopelagic crustaceans, and deep-sea fish sampled from remote South Pacific environments. The contamination does not remain restricted to one ecological level. It appears simultaneously throughout multiple layers of the food web, from drifting plankton to larger predators moving through darkness far below the surface. One of the most important transport mechanisms involves marine snow, the same slow rain of organic particles that sustains deep ocean ecosystems throughout the abyss. Tiny plastic fragments attach easily to this descending material, becoming incorporated into aggregates of dead cells, fecal pellets, mucus, and bacterial matter. As the marine snow sinks through kilometers of water, the attached plastics descend with it. What began as discarded material drifting near the surface eventually reaches the deep ocean floor through the exact pathways that evolved to deliver food. So the animals surrounding Point Nemo consume traces of human civilization not because they approached human environments, but because the ocean carried those materials to them. A copepod feeding within the mesopelagic zone cannot distinguish organic debris from synthetic particles suspended beside it. A deep-sea fish swallowing contaminated prey receives plastics already transferred upward through multiple feeding relationships. Even abyssal sediment communities encounter synthetic material settling gradually onto the seafloor around them. Sediment cores collected from remote abyssal plains across the planet now contain recognizable microplastic layers beginning during the middle of the 20th century, corresponding closely with the rapid global expansion of plastic production after the 1950s. Within geological records that normally preserve volcanic ash, fossilized microorganisms, and traces of climatic change, humanity has introduced a new marker horizon composed partly of synthetic polymers. Beneath Point Nemo, among some of the most isolated sediments on Earth, the same layer almost certainly exists already. The deep ocean remembers surface history with extraordinary patience. Material released into rivers, coastlines, or atmosphere eventually drifts outward through planetary circulation until even the most distant abyss receives some fraction of it. The creatures living beneath Point Nemo remain separated from humanity by immense distances of water and darkness, yet they still exist downstream from the industrial age. In the slow chemistry of the ocean, nothing released at the surface remains entirely local for very long. Far beneath the frozen crust of Europa, beyond the reach of sunlight, and far from the warmth associated with living systems on Earth, planetary scientists believe an ocean moves slowly in darkness. The moon's outer shell is thought to consist of ice between 10 and 30 kilometers thick, while the ocean beneath may extend downward for approximately 100 kilometers, deeper than any ocean on Earth. Jupiter's immense gravity flexes the moon continuously as Europa travels through its orbit, generating internal friction that prevents the hidden sea from freezing solid. No sunrise has ever touched that water. No atmosphere carries weather above it. If living systems exist there, they would survive without photosynthesis, without forests, without anything resembling the familiar surface ecology of Earth. For much of human history, such a possibility sounded impossible because life itself was assumed to depend completely on solar energy. The deep ocean changed that assumption permanently. Another moon, Enceladus, orbiting Saturn, offered even stronger evidence that distant oceans may not be sterile. During its mission through the Saturnian system, the Cassini spacecraft detected enormous plumes erupting from fractures near Enceladus's south pole. These plumes contained water vapor, ice grains, organic compounds, salts, and molecular hydrogen venting directly into space from the hidden ocean below the ice shell. That molecular hydrogen mattered enormously. On Earth, hydrogen appears around hydrothermal vent systems, where seawater interacts chemically with hot rock beneath the seafloor. The reactions release energy that chemosynthetic microorganisms use in place of sunlight. Entire ecosystems form around this chemistry, powered not by stars overhead, but by planetary heat and mineral exchange occurring in darkness. The plumes rising from Enceladus suggested similar reactions may be happening beneath its frozen crust at that very moment. Because of discoveries like these, astrobiologists increasingly look toward Earth's deepest marine ecosystems for guidance in understanding what alien life could resemble. Hydrothermal vent communities, abyssal archaea, sulfur metabolizing bacteria, and the slow biological systems inhabiting nutrient-starved trenches are now treated as analogs for environments beyond Earth. The organisms inhabiting the deep Pacific are no longer viewed only as unusual marine species. They have become models for how biology itself adapts when nearly every surface condition disappears. Point Nemo occupies a particularly important place in this understanding because its ecosystems survive under combinations of darkness, pressure, cold, isolation, and nutrient scarcity that once seemed incompatible with complex life. The water above the abyssal plain receives so little biological productivity from the surface that many regions resemble marine deserts. Yet organisms persist there anyway, surviving through efficiencies measured across evolutionary timescales rather than human ones. The lesson emerging from these environments is subtle but profound. Life does not appear to require sunlight specifically. It requires energy gradients, liquid water, stable chemistry, and time long enough for adaptation to unfold. On Earth's surface, sunlight became the dominant energy source because it was abundant. In the deep ocean, chemistry assumed that role instead. Every lanternfish migrating upward through darkness, every chemosynthetic bacterium oxidizing sulfur compounds, every archaean cell metabolizing ancient carbon beneath the sediment contributes another example of biology operating far outside conditions once considered necessary for survival. The ocean beneath Point Nemo demonstrates repeatedly that life can occupy environments defined not by abundance but by persistence. For planetary scientists, this changes the scale of possibility across the cosmos. Worlds once dismissed as frozen, dark, or geologically hostile now appear potentially habitable if liquid water and usable chemistry exist together long enough. Beneath ice-covered moons orbiting distant planets, hidden oceans may circulate through mineral-rich rock exactly as they do along Earth's seafloor. In that sense, the deep Pacific is more than a remote region of Earth. It is a working example of how living systems endure in conditions detached from sunlight and almost entirely separated from the surface world. The creatures drifting through the darkness near Point Nemo may resemble, more closely than anything on land, the kinds of life that could someday be found beneath oceans on worlds far beyond our own sky. Long before human beings mapped oceans, named continents, launched satellites, or measured the age of stars, lanternfish were already rising through the darkness beneath the Pacific in slow nightly migrations. Tonight, somewhere in the waters surrounding Point Nemo, those migrations continue exactly as they did tens of millions of years ago. The pattern is older than the Himalayas, older than the Atlantic Ocean in its current form, older than most living lineages on land. Small bodies ascend toward faint surface waters under cover of darkness, then descend again before dawn, repeating a cycle inherited across spans of time so immense that entire branches of terrestrial evolution unfolded while it remained unchanged. Elsewhere, on the abyssal plain, giant isopods move patiently across the sediment with body plans that would have appeared familiar during the Jurassic period. Their armored segments, compound eyes, and methodical scavenging behavior have persisted through asteroid impacts, continental drift, mass extinctions, and climatic upheavals that erased countless other forms of life. When dinosaurs vanished from the continents above, these deep-sea crustaceans continued almost uninterrupted in the darkness below, insulated from many of the rapid environmental transformations shaping the surface world. Even slower lives unfold beneath the sea floor itself. Deep within the compressed sediment under Point Nemo, archaea metabolize traces of organic material that settled through the water column thousands of years ago. Some divide so gradually that a single cellular generation extends across the entirety of recorded human civilization. While kingdoms rose and collapsed on land, while languages formed and disappeared, while coastlines filled with cities and electric light, these microorganisms persisted at nearly immeasurable metabolic rates, exchanging energy so slowly that biology begins to resemble geology. The abyssal plain surrounding them accumulates change with similar patience. Manganese nodules scattered across the sediment grow only a few millimeters over spans of time measured in millions of years. Layer by layer, dissolved metals precipitate onto their surfaces around tiny nuclei such as shark teeth, volcanic fragments, or microscopic debris from vanished organisms. The outer surface of a nodule resting on the seafloor today may have begun forming before the earliest members of the human genus existed at all. To disturb one is to interrupt a process operating on timescales beyond ordinary comprehension. Far above those nodules, Antarctic bottom water continues its silent movement through the deep Pacific Basin. The water presently flowing beneath Point Nemo may have touched the Antarctic surface centuries ago before cooling, sinking, and beginning its slow journey northward across the abyss. Entire civilizations emerged, transformed, and disappeared during the transit of a single parcel of deep ocean water from polar winter to the remote Pacific floor. Beneath all of it lies the sediment column itself, preserving records from epochs unimaginably distant from the present moment. Buried within those layers are traces of ancient atmospheric transformations, signatures from mass extinction events, microscopic remnants from oceans that existed before complex animals evolved, particles from the asteroid impact that ended the age of nonavian dinosaurs settled eventually through seawater and became part of the same geological archive. The deep Pacific floor remembers events separated by hundreds of millions, even billions, of years, holding them quietly beneath kilometers of cold water and slowly accumulating clay. Against these scales, the surface world appears startlingly brief. Human civilization measures itself through elections, lifetimes, economies, inventions, and generations. Cities rise within decades, technologies transform within years, languages shift within centuries. Yet, beneath Point Nemo, the dominant rhythms are glacially slow, governed by circulation cycles, sediment deposition, evolutionary persistence, and chemical processes unfolding across geological time. The creatures inhabiting this darkness are not adapted to urgency. They are adapted to endurance. Their world changes so gradually that entire chapters of human history pass almost invisibly above them. Brief disturbances crossing the surface of an ocean system that has already outlasted nearly everything Earth has ever created. Maps gave the region a name that reflects human distance from land, but the word loneliest belongs more to our psychology than to the ocean itself. It describes the sensation a person might feel standing at the edge of an empty horizon, with no sign of another human presence for thousands of kilometers in every direction. The coordinates we call Point Nemo did not invent that feeling. They simply became a place onto which human beings projected it. The life inhabiting those waters has never experienced isolation in the way humans understand it. No lanternfish rising through the mesopelagic darkness perceives itself as abandoned. No Archean cell buried beneath abyssal sediment understands separation from cities, coastlines, or civilization. The ocean at Point Nemo is not waiting for companionship. It is occupied continuously by living systems following rhythms older than humanity itself. Within the sediment, beneath the abyssal plain, bacterial populations exist in astonishing density. Thousands of microorganisms inhabit volumes smaller than a fingertip, exchanging chemicals, metabolizing ancient carbon, reproducing slowly, and participating in biological communities so compact and interconnected that the concept of solitude becomes meaningless there. Beneath the apparently empty seafloor lies a crowded, microscopic world that has persisted uninterrupted across spans of time difficult to imagine clearly. Higher in the water column, lanternfish drift upward each night, surrounded by vast populations of their own kind. Their migrations unfold collectively, billions of bodies responding to fading surface light in synchronized movement through the dark Pacific. The migration route surrounding Point Nemo may be thinner than in nutrient-rich oceans elsewhere, but it is still part of a planetary biological pulse that has repeated for tens of millions of years without interruption. Generations vanish and are replaced, while the pattern itself continues unchanged. Even the archaea deep beneath the sediment are not isolated organisms in the human sense. They form immense continuous microbial networks extending across abyssal plains, separated by enormous geographic distances, yet connected chemically through the slow movement of water, minerals, and organic compounds. Their environment appears barren only from the perspective of large surface animals. At microbial scales, it is structured, inhabited, and alive with interactions unfolding far beneath human perception. What Point Nemo lacks specifically is human presence. There are no shipping corridors crossing overhead in constant traffic, no coastal cities brightening the horizon, no industrial noise saturating the water column, no permanent observers remaining there to witness what lives below. Human absence became the defining characteristic because humans were the ones naming the place. That absence may also explain why the ecosystem remains so intact. In many parts of the world's oceans, biological systems now exist beneath the constant influence of shipping, extraction, fishing pressure, chemical runoff, and mechanical noise. Point Nemo remains comparatively untouched not because it resisted humanity deliberately, but because reaching it is inconvenient even by modern standards. Distance preserved it accidentally. The name itself carries another layer of irony. Hervoya Lucatella chose Nemo in reference to Captain Nemo from Jules Verne's 20,000 Leagues Under the Seas, a fictional figure who withdrew from human civilization and sought refuge beneath the ocean. The association feels fitting from a human perspective because the coordinates appear distant, unreachable, detached from ordinary life. Yet the creatures inhabiting the real Point Nemo never fled anything. They did not retreat from civilization, escape conflict, or seek solitude. Long before any human language existed to describe loneliness, they were already there beneath the Pacific, moving through darkness, exchanging energy, reproducing, feeding, migrating, glowing, listening, and surviving according to the ancient rules of the deep ocean. In the end, the loneliness associated with Point Nemo belongs almost entirely to us. It is a reflection of how humans interpret distance from themselves. The ocean does not share that interpretation. Beneath the cold water and slow currents, life continues without reference to human absence at all, complete within its own immense and ancient world. Most of what humanity understands about Point Nemo has been assembled indirectly, through fragments gathered from instruments passing briefly through the region rather than through continuous observation. The water column at those coordinates has never been systematically explored from surface to seafloor by remotely operated vehicle. No uninterrupted visual descent exists, showing every layer, every migration, every organism occupying the immense vertical distance between sunlight and abyssal sediment. What science possesses instead are scattered glimpses collected through methods that reveal certain forms of life while obscuring others almost completely. Trawl nets, among the oldest tools in marine biology, capture fish, crustaceans, and rigid-bodied organisms relatively well. Yet the same nets tear fragile gelatinous animals apart so thoroughly that many dissolve into unrecognizable tissue before reaching the surface. Jellyfish, siphonophores, salps, and comb jellies, organisms now believed to dominate enormous portions of the open ocean biomass, remained underestimated for decades because the technology used to study them destroyed them during collection. Every historical trawl survey through the deep Pacific therefore contains an invisible absence, entire communities reduced to fragments that could not be counted properly. Acoustic surveys carry different limitations. Sonar systems detect animals efficiently when those animals contain gas-filled structures, such as swim bladders, that reflect sound waves back toward the instrument. Soft-bodied gelatinous organisms often pass through acoustic monitoring almost invisibly because their tissues resemble seawater too closely. A drifting pyrosome colony, many meters long, may occupy the water column while remaining nearly transparent to sonar. The deep Pacific contains living forms that evade detection not through camouflage evolved against predators, but because the tools humans designed were never suited to perceiving them clearly. Sediment cores provide another narrow perspective. Cylinders of mud extracted from the abyssal plain preserve microorganisms, chemical signatures, microfossils, and traces of benthic life inhabiting the seafloor itself. They reveal ancient climate shifts, microbial metabolism, cosmic particles, and layers deposited across geological time. Yet the immense water column above remains absent from those samples. The migrations of lanternfish, the drifting chains of salps, the flashing signals of bioluminescent predators, all disappear entirely within a sediment core, leaving behind only the faintest indirect traces of their existence. Even the spacecraft graveyard resting near Point Nemo remains largely hypothetical in biological terms. Decades have passed since pieces of Mir, cargo vehicles, rocket stages, and other orbital debris settled onto the abyssal plain, introducing hard surfaces into one of the softest seafloor environments on Earth. Deep sea ecology strongly suggests those structures are now colonized by bacterial films, sessile invertebrates, scavengers, and slow-growing biological communities adapted to metal surfaces under crushing pressure. Yet no imaging expedition has visited the core debris fields directly. The ecosystems likely developing there remain unseen. Marine ecologists use the phrase dark biodiversity to describe species known to exist statistically within ecosystems, despite remaining undetected by direct observation. Point Nemo may contain more dark biodiversity than almost any marine environment on Earth. Every expedition into remote abyssal regions consistently returns with organisms previously unknown to science. Hundreds of new deep-sea species are formally described each year, and the pace of discovery continues accelerating in the least explored locations. The implication is difficult to avoid. Somewhere within the water column surrounding Point Nemo, animals almost certainly drift, hunt, reproduce, glow, and die without ever having entered human awareness. Some may have been brushed aside unnoticed by trawl nets. Others may remain acoustically invisible, chemically subtle, or visually inaccessible within darkness too immense for current exploration efforts to cover thoroughly. At those coordinates, there are likely living organisms that possess no scientific name, no formal description, no image, and no place yet within biology's catalog of Earth. They exist presently not as confirmed discoveries, but as absences inside the data itself, empty spaces where evidence suggests life should be waiting in the dark, beyond the limits of what humanity has managed to observe. For years, after the sound echoed through the hydrophone network, the Bloop occupied an unusual space between science and imagination. Researchers knew the signal was real. It had crossed thousands of kilometers through the Pacific and arrived on multiple listening stations with enough intensity to place it among the loudest acoustic events ever detected underwater. Yet no known animal matched its amplitude, and no existing catalog contained a geological signature quite like it. The mystery endured not because the ocean had produced something supernatural, but because human understanding of the deep sea remained fragmentary enough that an Antarctic ice fracture could move through the Pacific undetected as an unidentified phenomenon for more than a decade. When the explanation finally arrived, it changed the meaning of the event. The Bloop had not revealed an undiscovered leviathan hidden beneath the South Pacific. Instead, it exposed how incomplete the acoustic map of the ocean still was. Vast structures of Antarctic ice had been breaking, grinding, and transmitting sound through the SOFAR channel for unknown spans of time before researchers recognized the pattern clearly enough to identify it. The unfamiliarity belonged not to the sound itself, but to the limits of the listening systems and reference databases humans had constructed. The ocean continues, producing sounds that remain uncatalogued. Hydrophone arrays monitor only a fraction of the world's seas, and even within monitored regions, the distinction between biological, geological, and mechanical signals is not always obvious. Deep water carries echoes from earthquakes, submarine landslides, collapsing ice shelves, whale migrations, volcanic activity, shifting sediment, storms crossing distant surfaces, and the movements of countless organisms still poorly studied. Recordings accumulate faster than definitive explanations. Some acoustic events are likely already sitting within archival data, labeled only as unidentified because nothing comparable exists for confirmation. A sound produced by an organism never formally documented would not announce itself clearly as biological. It would appear simply as an anomaly without a matching signature. The same applies to unfamiliar geological processes occurring under pressures and temperatures rarely observed directly. The history of deep ocean science repeatedly demonstrates how easily absence of evidence becomes mistaken for evidence of absence. Chemosynthetic ecosystems were once considered impossible because biology assumed sunlight was essential for complex food webs. Living coelacanths were believed extinct for tens of millions of years until fishermen brought one to the surface alive. Hadal trenches were thought incapable of supporting vertebrate life. Before snailfish were filmed, thousands of meters below expected physiological limits. Giant siphonophores drifted through the open ocean long before remotely operated vehicles revealed their actual size. Again and again, the deep sea has overturned confident assumptions, not through small corrections, but through discoveries that forced entire frameworks of understanding to expand. Biology underestimated the resilience of life, the range of viable ecosystems, the adaptability of cellular chemistry, and the scale of organisms hidden within darkness. Each revision emerged only after new tools finally allowed humans to perceive environments previously inaccessible. Point Nemo occupies one of the least directly observed regions in that already underexplored world. The prevailing assumption has often been that extreme oligotrophy limits the region severely, reducing it to sparse microbial life and scattered larger organisms surviving at minimal densities. The logic appears reasonable when viewed from surface productivity alone, yet much of deep-sea science consists precisely of reasonable assumptions later revealed to be incomplete. A truly systematic survey of Point Nemo, combining continuous visual descent, long-duration acoustic monitoring, environmental DNA sampling, and direct observation of the abyssal plain, has never occurred. Until it does, conclusions about the region remain provisional, assembled from partial methods looking briefly into an environment operating continuously beyond observation. The Bloop ultimately left behind a quieter but more enduring realization. The mystery was solved, but the deeper uncertainty remained untouched. Human beings do not yet know fully what exists in the waters surrounding Point Nemo. We know only what our limited instruments have managed to glimpse so far, and the history of the deep ocean suggests those glimpses are rarely the whole story. Seen from orbit, Point Nemo does not appear unusual. There is no visible boundary around it, no change in the watercolor dramatic enough to announce that this patch of ocean is farther from human settlement than any other point on the planet. Clouds pass over it without distinction. Storm systems rotate across it the same way they rotate across every ocean basin. Sunlight scatters across its surface in shifting silver bands, indifferent to coordinates and names. Yet, beneath that ordinary appearance lies one of the clearest reminders that the human world occupies only a fraction of Earth's total reality. The distance separating Point Nemo from the nearest shoreline is often described as isolation, but distance alone is not the most important fact. The more profound reality is that an immense portion of the planet has organized itself entirely without reference to human life. Ocean circulation, abyssal chemistry, evolutionary adaptation, sediment accumulation, microbial exchange, and deep biological time continued for hundreds of millions of years before a human being ever calculated these coordinates or attached meaning to them. Point Nemo feels remote because it exposes the scale at which Earth exists independently of us. Human civilization occupies coastlines, river valleys, plains, and elevated regions touched by sunlight and atmosphere. The deep ocean belongs to another set of conditions entirely. Most of the planet is covered by water, and most of that water extends downward into darkness deeper than mountains are tall. The abyssal Pacific surrounding Point Nemo is not a rare exception within Earth's structure. It is one of the dominant forms the planet takes, hidden only because human life evolved at the surface. At any given moment, the closest human beings to Point Nemo are often not sailors crossing the South Pacific, but astronauts aboard the International Space Station, passing overhead hundreds of kilometers above the ocean's surface. Suspended within aluminum walls and recycled air, they move through a vacuum environment the human body was never designed to survive. Beneath them, 4 kilometers below the ocean's surface, lies another environment equally incompatible with unprotected human life, crushing in pressure instead of empty in pressure, cold instead of sunlit, saturated with seawater rather than exposed to cosmic radiation. In different directions, both environments reveal the same truth. Human beings persist there only through carefully engineered systems, separating fragile biology from hostile physics. The resemblance deepens in quieter ways. Astronauts looking down from orbit can observe continents, storms, and cloud bands, but the deep ocean remains hidden beneath the reflective skin of the sea. The abyssal plain below Point Nemo exists beyond direct sight, even from space. Human technology has photographed distant galaxies more thoroughly than portions of Earth's own seafloor. Scattered across that seafloor are fragments of machines built for entirely different ambitions. Pressure vessels from Progress spacecraft, sections of transfer vehicles, fragments of station hardware, and the remains of Mir descended through the atmosphere, trailing heat brighter than molten metal before vanishing beneath the Pacific surface. Their final movement carried them downward through cold water into darkness, older than human civilization itself. What happened afterward unfolded without witnesses. Metal surfaces that once orbited above the planet encountered soft abyssal sediment where hard structure is rare. Bacteria spread across titanium and steel. Sessile organisms attach themselves to exposed surfaces. Mobile scavengers cross the sediment around the debris fields. Slowly, without intention or symbolism, machines designed for spaceflight entered the ecological processes of the deep sea. The transformation carries a strange calmness to it. Human engineering, after crossing vacuum and fire and ocean, became substrate. The remote Pacific did not preserve the wreckage as monuments, nor reject it as foreign intrusion. It absorbed the material into ongoing biological cycles that had already been operating for geological ages before the first rocket ever left Earth. At the sea floor beneath Point Nemo, there is no sunrise. No dawn moves across the abyssal plain. No plant reaches upward through the dark, searching for light. The creatures living there inherited a world where the sun effectively does not exist, and yet the water remains inhabited from the sediment below to the open water above. Tiny archaea persist within buried layers of clay. Lanternfish rise and fall through the mesopelagic in ancient migrations. Dumbo octopuses drift above the seafloor with slow movements of their fins. Giant isopods wait motionless beside the sediment for the arrival of food that may not come for years. Life continues in a place that appears, by surface standards, completely unfit to sustain it. For most of human history, biology assumed that sunlight stood at the beginning of every living system. Forests, grasslands, coral reefs, rivers, and surface oceans all trace their energy back to photosynthesis. Even predators feeding at the highest levels of the food chain ultimately depended on plants converting light into stored chemical energy. The deep Pacific challenged that assumption gradually, then completely. Whale falls demonstrated that ecosystems could survive for decades from a single descending carcass. Chemosynthetic bacteria revealed that metabolism could be driven by hydrogen sulfide and methane rather than sunlight. Archaea buried beneath abyssal sediment showed that life could persist at metabolic rates so slow they bordered on geological process. The temperatures surrounding Point Nemo remain only slightly above freezing, generally between 1.5 and 2.5 degrees Celsius. In surface environments, such cold slows biological activity sharply. Yet the deep Pacific has operated under these conditions for millions of years. Cellular membranes adapted, enzymes adapted, blood chemistry adapted. Entire evolutionary lineages shaped themselves around cold stability rather than warmth. The creatures living there are not enduring those temperatures as hardship. For them, the cold is normal. The same is true of pressure. At abyssal depth, every square centimeter experiences forces that would collapse unprotected human bodies instantly. Yet, soft tissues filled with water experience little internal compression because water itself resists compression. Snailfish, octopuses, gelatinous colonies, and deep crustaceans move through these pressures with no awareness that surface life would consider them catastrophic. The conditions that appear impossible from above become ordinary once life has enough time to adapt to them. Point Nemo is also separated from nearly every nutrient source associated with coastal oceans. No major river systems deliver mineral runoff there. No continental shelf funnels abundant productivity into the region. Surface waters inside the gyre remain among the most nutrient-poor on Earth. Still, life persists through patience and efficiency. Marine snow descends continuously from above. Antarctic bottom water transports dissolved chemistry through the abyss. Whale carcasses become century-long ecosystems. Chemosynthetic microbes draw energy from inorganic compounds hidden within the seafloor itself. Nothing is wasted because almost nothing arrives quickly. Perhaps the most important detail is that none of this depends on humanity in any way. The ecosystems surrounding Point Nemo existed before its coordinates were calculated, before hydrophones recorded the bloop, before spacecraft fragments descended through the Pacific atmosphere, before microplastics entered the sediment. The deep ocean did not wait for human discovery to become biologically complete. It was already operating according to physical and chemical rules far older than civilization. When these observations are gathered together, they lead quietly toward a larger conclusion. Life requires chemistry capable of storing and transferring energy. It requires liquid water in which those reactions can occur. And above all, it requires time, because evolution works through accumulation so gradual that entire mountain ranges can rise and erode while adaptations slowly refine themselves generation by generation. Those conditions may not be unusual. Beneath the ice shell of Europa, within the hidden ocean of Enceladus, beneath distant frozen crusts orbiting other stars, liquid water and chemistry may already coexist in darkness beyond sunlight. Point Nemo suggests that where those conditions persist long enough, biology may emerge not as a miracle, but as a natural continuation of physics and time. There is no marker floating above Point Nemo, no buoy anchored to the coordinates, no island breaking the horizon, no lighthouse, shipping lane, research station, or fixed platform waiting in the open Pacific. The coordinates exist only as mathematics, layered onto water, a human geometry projected across an ocean that does not recognize borders or names. If a vessel crossed those exact coordinates under clear weather, the crew would see only the same immense surface extending outward in every direction, blue merging into blue, until distance and atmosphere erased the boundary between sea and sky. The location itself offers nothing visually distinct. Waves rise and collapse according to wind and pressure systems moving across the South Pacific. Clouds cast shifting shadows over the water. Sunlight scatters across the swells during the day, then disappears each evening into darkness that seems complete at the surface, but is almost insignificant compared with the darkness below. Beneath the hull, the water descends for 4 kilometers before reaching the abyssal plain. Temperature falls steadily toward near freezing. Pressure builds layer by layer until it reaches approximately 380 atmospheres, forces immense enough to collapse ordinary structures instantly. Sunlight vanishes entirely within the upper fraction of the descent. Beyond that point, the ocean becomes a world defined not by vision, but by chemistry, pressure gradients, drifting organic matter, and faint pulses of biological light. Somewhere within that darkness, lanternfish are already moving upward through the water column. Their migration began long before human beings existed and continues with almost no alteration across evolutionary time. Every night, they rise toward shallower depths to feed, then retreat downward again before daylight reaches the upper ocean. The movement repeats with planetary regularity, billions of small bodies ascending and descending through black water in rhythms older than most modern ecosystems on land. Elsewhere, in the same darkness, a siphonophore extends its tentacles through the water like drifting threads suspended in slow current. A Dumbo octopus crosses above the sediment with soft, deliberate motions. A vampire squid waits within oxygen-poor water that excludes most predators. Far below them all, within compacted sediment, archaea metabolize traces of carbon descending from surface waters thousands of years earlier. Their existence unfolds so slowly that a single cellular generation can span the entirety of recorded human civilization. None of these organisms possesses any awareness that human beings consider this region lonely. Loneliness requires imagination, memory, comparison, and the recognition of absence. The deep Pacific contains none of those things. It contains cold water circulating through abyssal basins. It contains mineral sediment accumulating grain by grain across geological time. It contains chemistry capable of sustaining metabolism, and within those conditions, life continues because life adapts to whatever stable reality surrounds it long enough. Even now, the exact biological composition of Point Nemo remains unresolved. No expedition has systematically descended from surface to seafloor directly through the coordinate itself, documenting every layer of the water column. Trawl nets miss soft gelatinous organisms. Acoustic systems overlook acoustically transparent bodies. Sediment cores reveal only fragments of benthic existence. Entire communities may remain undescribed simply because no instrument has yet observed them intact. The coordinate, therefore, remains open in the truest scientific sense, not empty, but unfinished, a location carrying more absence of data than absence of life. Somewhere below the Pacific surface, at those remote coordinates, unrecorded organisms continue feeding, reproducing, migrating, glowing, drifting, and evolving beyond observation. And until human beings finally descend through that darkness and look directly into it, the most complete answer to what lives there will remain where it has always been, suspended quietly in the cold water beneath the open South Pacific,